So in a previous lecture, I explained a naive approach that we just augment the encoding of coming from transformer with the encoding coming from the knowledge base and create a better encoding. But this is naive. Why don't we just use as a node in knowledge base? Why don't we use that your sentence as just a node in knowledge base? This is more, this is in harmony with what is in our brains. So we should do that, in my humble opinion. So I want to explain this article by Percy Liang. I also know Yuri Leskovic. He's interested in GNN, graph neural networks. Percy Liang is expert in semantic parsing. I've explained his articles, for example, using Freebase and other researchers. So there are two facts. Why language models have a broad coverage of knowledge? They do not empirically perform well in structured reasoning. As I said in the previous lecture, because they don't appreciate the semantic relations that we humans use. It's just good for structural things and the wolves of Noam Chomsky. But knowledge graphs, such as ConceptNet, Atomic, for common sense reasoning, are more suited for structured reasoning. So if we combine language models with knowledge graphs, it produces two challenges. So the problem of answering questions using knowledge pre-trained language models and knowledge graphs presents two challenges. Given a question answering context, for example, you have your answer is just answer choice, we have 4 answers, the methods need to identify relevant knowledge from the large knowledge graphs. And also they should perform joint reasoning over question answering. So we address the above challenges through 2 key innovations. First, relevance scoring, where we use language models to estimate the importance of knowledge graph nodes relative to the given question answering context. And joint reasoning, where we connect the question answering context and knowledge graph to form a joint graph and mutually update the representation through GNN. So you can consider this sentence, all of these sentences, as just one node of this knowledge graph. So you see how meaningful everything is, how we can reduce the complexity of our problem, how we can synchronize and align the world of sentences with the world of knowledge bases. So this is the architecture. You create the probability score, use graph neural networks, because we know the structure, we know the knowledge graph, so there's no parsing here that we should first, for example, find AMR parsing in order to have a graph. Here we already have a graph because it's our knowledge base. So that's why we can represent it, all the nodes, easily and create a probability score for any question and answer. So this is an overview. We have 2 key insights: relevance scoring and joint reasoning. So we use language model to see the relevance of given a condition on your context, that sentence, what is the relevance of any of these entities, such as bank, any of these entities. So you can look at it like an input-output, and you can easily find that. So this is the QA knowledge graph node relevance scoring, and you can compute the relevance score by this. This is text of V. So this one denotes the probability of text computed by the language model. So this relevance score captures the importance of each knowledge graph node relative to the given question answering context. And the architecture of graph neural networks. I have a playlist for graph neural networks. I think we should combine graph neural networks with factor graph message pathing to have a better graph neural networks. Transformer is just a special case of graph neural networks. So if we combine graph neural networks with factor graph and message passing, we have a better updates for nodes, and it's good for both node information and relation information. Even for relational GNN, it's very good. So this is what I really think about it. Because message passing is a process, and gods create processes rather than algorithm. So they're indirectly calculate and compute things, while human just creates algorithm without creating processes. For example, DNA in your body is language of your body. It does some processes, proteins, enzymes. It's like a structured graph, and everything is in a process. For example, the potassium raises or calcium decreases, something bad happens in the body. So everything is in process. And the reason that I like factor graphs and message passing is exactly the same thing, because the message passing process is not only an algorithm but also a process that you can implement. So it's very interesting. So we can create these representations for using score-aware attention. And for inference and learning, we use the information from both the question answering context and the knowledge graph. So this is the probability of your answer given your question. It's a multi-layer perceptron of Z of language models, Z of the GNN and G. And G is just the pooling of your hidden representations. And this is the visualization. You see how interesting it is. So they represent the context here, but I think we can also simplify this approach in this article even more by trying to simplify the context. Care about the semantic stuff as I've explained in playlist for semantic parsing.